Hello, everybody. So this week we're talking about two learning targets in our Unit 2. One is called optimization, which means maximizing the benefits of in a particular function. Usually that means finding the maximum. I mean, if profit is the y value, then you want to maximize that. Or if cost is the y value, you want to minimize that. So we're really finding the maximums and the minimums. But the struggle here is creating the actual function. And then inverses, which is very just math algebra heavy. So if you like solving for x, then you're going to like that one. But today and tomorrow, optimization. And here's just a very quick example. This is a very, very typical problem with optimization. The overall goal is that you're going to have to read and understand some sort of small paragraph, and you're going to mathetize it. You're going to write an equation that is relevant to the context of that problem, and then use your technology to solve it. So, for example, this you're going to hear this problem a lot. You are a farmer and you have to build a pen to keep your animals in, and one of the walls is a river, acting as a river. You only have 750 yards of fencing. And you're going to build this rectangular fence, but you don't need four sides because the river is acting as that fourth side. So what are the dimensions going to be so that you actually maximize the area of this pen? You could realize you could have this length to be 1 yard long and this length over here be 1 yard long. So you've used 2 yards. That means this long piece would have to be 748 yards long. Now that would have a particular area, but what's the magic combination of these two sides and this length to have the biggest area? Well, you don't know how long that's going to be, so we'll just let that equal x. And if you use x amount of your yards here and x amount of your yards here, then you've used 2x. And how much do you have left over to create this third and final part? You have 2x less or less than 750. So in other words, 750 minus 2x would be this length right here. And then you want to, so here are the abstract dimensions, but we're going to find the my dog wants to come in, she wants to leave, she wants to come in, she wants to leave, so I just locked her out. Okay, so we want to find the area of this rectangular pen, but we want to find the biggest area. Well, thank goodness it's a rectangle because we know exactly how to find the area of a rectangle. It's length times width. And the length happens to be this 750 minus 2x, and the width is x. It really doesn't matter since multiplication is commutative. So I multiply both dimensions, x times 750 minus 2x. And the domain, realize, is the x value is everything between 0 and 750. You can't let x equal 800 because you just simply don't have enough fencing material to create a length of 800 here. So your x has to be even less than that, less than 375. Because 375 times 2 will get you 750. If this side is 375, then automatically this side is 375. And that's all 750 yards of your material. So you don't even have enough material to create this third side. So your domain has to be less than 375. So that's why you have the parentheses here, not a bracket. Okay, so now what do you do? This is, believe it or not, this is the hardest part. If you can get this, then you're going to be great. From here on out, the technology is doing all the hard work. You're going to graph this and then find the maximum. Notice x times 750 minus 2x is equaling the area. So the y value is the area. And here is the maximum of that quadratic. The max y value is 70,312. So that is the greatest area. And that occurs when x is 187.5. So when this distance is 187.5, so will this one be. And then take 750 minus 2 times 187.5 to figure out this length. And here's the whole answer right here. So this is the final answer, all of this. You have the dimensions, you have the area, and actually this sentence right here, don't forget it's 70,000 yards squared, so that is definitely necessary. But this final sentence is the answer, and everything above it is the work that supports it. So again, you read a little paragraph, drawing a picture almost always helps, and then create a mathematical function. Once you get the function, you graph it on your device, which is required, your calculator, and you use the device's technology to find what you need to find. So we got two examples for us. So this one, find two positive numbers whose sum is 10, and the product of one of the numbers and the square of the other is the greatest. So that's a lot of words, and it takes me a few times to read this before I understand even what is being asked. So break it down. Find two positive numbers. That's what you're finding. That's going to be your answer. You need to find two positive numbers. So I'll just give them names, A and B. And I know that whose sum is 10. So the sum of these two numbers must equal 10. That's mathematically, that's A plus B equals 10. I don't know how I'm going to use that yet, but that's what that means. The two numbers that I'm thinking about have to add up to 10, and they have to both be positive. So the domain for A and B, the A and B have to be in this interval between 0 and 10. It could be 1 and 9, it could be 2 and 8, it could be 3 and 7, it could be all sorts of things. But A and B have to be positive, and they have to add up to 10. And then it says the product of one and the square of the other is the greatest. So that may take a little bit of thinking through. So here are some examples. Like whenever I get confused with a word problem, I just think about these what if statements. What if one of the numbers was 1 and one of the numbers was 9? Well, product means multiply. So if I multiply 1 and the square of the other, what do I get? Well, in this case, 1 times 9 squared is 81. Well, what if I squared the first one and multiplied it by 9? Then I would get 9. Two other numbers are 2 and 8. 2 plus 8, they're both positive and they add to 10. So 2 squared times 8 is 32, but 2 times 8 squared is 128. So now I'm getting a better idea that, okay, so now it wants me to find a combination of two numbers that are both positive. They add up to 10, and if you multiply them, but one of them is squared, which combination is going to give you the biggest answer? So far, it's 2 times 8 squared. That's my biggest answer so far. 128 is the biggest. And then there's also 3 and 7. 3 times 7 squared and 3 squared times 7. Well, I get 147 and 3. So now 147 is in the lead. And this is not really an efficient strategy. It's good to always be able to generate some possibilities, but it should not be, it's not really an efficient strategy, because think about how many numbers add up to 10 that are positive. I mean, did you think about this? 6.5517 plus 3.4483. If you add these two, they add up to 10. And if I square one and multiply by the other, what do I get? So just guessing and checking is not a solution. And it's not going to be any credit if the way you get the correct answer is by guessing and checking. That won't be any credit. We have to do this in a more sophisticated way. But this did help me understand what's going on. I multiplied two numbers. One of them is squared. Well, my two numbers are A and B. So I can either take A squared times B or B squared times A. This is the same difference. And I need that to equal the greatest possible answer. All right. Well, remember, so realize this equation right here has three unknowns. You've got A, which you don't know, B, which you don't know, and then the answer to the multiplication, which you don't know. So that's three things, three variables. And you almost always want to squeeze three variables down to two, almost always. And you do that. Actually, we did that with the fence problem. Like here, there were really two variables. There was this dimension and this dimension. So I could call this x and I could call this y. And x times y would equal the area. But I didn't write this as y. I wrote it as a combination of this first variable. I didn't write it as just something new like y, some unknown. I wrote it as 750 minus 2 times x. So I incorporated this first variable. So that means that I only had this one variable x. That's what I'm going to do here. A plus b equals 10 implies both of these things, doesn't it? I could subtract a on both sides and get b equals 10 minus a. Or I could subtract b on both sides and get a equals 10 minus b. So all three of these equations say the exact same thing. And so, but this is the key here. And it doesn't matter which one you choose, but I just chose 10 minus a. So I replaced b, a squared times b. So I'm using this first one. Again, it doesn't matter which one, but I did a squared times b. But instead of using b, I used 10 minus a. And that's really a key part of this, is when you fuse together or converge two expressions to get one. And now you have something that you can actually graph. So instead of a, I'll just replace that with x. And instead of the greatest possible answer, I'll replace that with f of x or y. So I'm going to graph this. This is the hard part. If you can get here, you're doing great. The rest of the technology will take care of. So you graph this and you want to find the biggest y value that this will ever produce, but only in the domain from 0 to 10. Because it wouldn't make any sense to have a equal 13. That would mean b would have to equal -3, because remember, they have to add up to 10. They both have to be positive. So I go to my graph, and here's my inspire. So I just do x times parentheses 10 minus x. One of these was squared. The first one was squared. So x squared. And notice I did not multiply it out. And don't multiply it out, because that's going to be a time waster. You do not have to multiply it out. This is totally fine. You're leaving it factored. And you graph that. And here's the graph I got. So here's 10. This is x equals 0, and here's x equals 10. So I'm only focused between these two numbers, and my maximum is way, way up there. And dragging up there is not efficient. We would change the window settings. Some people like to use zoom out, which you could start there, but try to graduate to the window settings. You want to see up there. Well, up implies y. So you need to change the y on your window. So window zoom, escape, go to menu, window settings, there it is, and a bunch of digits. I don't care. All I focus on is y max. Right now, my ceiling, my y max is 23, and let's just jump up to 200. Aha, 200 will be just fine. So if 200 didn't, if I still didn't see the hump at 200, I would have gone up to 400 or something. So again, here's when x equals 0, here's when x equals 10, and I want to find this maximum, this relative maximum right here. So I go to my tool and analyze graph. I'm going to find the maximum. It's asking for the lower bound, so I click enter. Then the upper bound, I click enter, and there it is. The greatest possible answer is 148, and that occurs when one of the numbers is 6.67. So here's that graph that you just saw, and you had to interpret this correctly. Remember what x and y equal. X represents the a value. Remember, a was one of my positive numbers, a plus b equals 10. And then the y is the greatest possible answer. So 3 times 7 squared was really close. That was 147. I know mathematically that 148 is actually the greatest number achievable. And that occurs when one number is 6.67. It's actually 6 2/3, which makes the other one 3 1/3. because they both have to add up to 10. So I just subtracted from 10. And I get this paragraph is the ultimate goal, and everything above it is the work that supports it. One more. This is a classic problem for our class. You're going to see this. I can practically guarantee it's going to be on the test. So it's almost cheating that you're seeing this right now. You've got a rectangular sheet of metal that's 12 by 20 inches. That's the dimension of that rectangular sheet right here. And what you're going to do is you're going to take some shears and you're going to cut a corner of equal size from all four corners. And imagine a corner being cut, all four corners being cut. And then can you imagine the two sides fold in and the two other sides fold up? And you would create this box right here. So the question is, how big of a square could you cut out, or should you cut out, so that when you fold it all up to get this box, you get the biggest possible box? That's the question. And first, let's realize that we are finding the biggest possible box. The box is a three-dimensional object, so we're finding the volume, which is length times width times height. And for this box right here, I chose this as the length, I chose this as the width, and I don't think I would get any arguments that this is the height. But what do I plug in here? Because I can't put this in my calculator and press enter. It has something to do with 20 and 12. Well, again, back to this sheet. Imagine physically cutting out the square. How big of a square would you cut out? You don't know. So we're going to let that equal x. I would cut out an x length. So this is a square that's x by x. And when I cut those four corners out, you can fold in these two sides, which would correspond to this side, and then fold up the two long sides, which would correspond to this side and this side. So now can you see what the length is? What is this yellow distance? It corresponds to this, right? It was originally 20 long, but then I cut off an x here and I cut out an x here. So this length is really 20 minus 2x long. It depends on what x is. And then what about the width? How wide is this? Well, it's definitely under 12 because this original was 12 inches long. And I cut out an x here and I cut out an x here. So now this remaining portion is 12 minus 2x. And then what's the height? Well, when you fold these up, can you see how this distance, this x distance, gets folded up and it becomes the height? So there's the height. And I've got the volume. I've got length times width times height. And now I graph. So I go to my calculator and I get a new page. I want to graph. So I do 20 minus 2x. Don't forget to press multiply. I think the Inspire is very particular about that. Multiply by x. Don't distribute, just you can leave it in factored form. And there I have it. So what are these zeros here? This is the number 1, 2, 3, 4, 5, 6. So the number 6 is a 0. Hopefully that makes sense, because if you cut out a square that's 6 inches long, well, if you cut it out 6 inches here and 6 inches here, then you'll have 8 inches left over because this dimension was 20. But if you cut out 6 inches from this side and this side, this was only 12 inches long to start off with. So if you cut off 6 here and 6 here, this becomes 0, a 0 width. So that's why it shows a 0 width right here. So that tells us the domain. The domain has to be between 0 and 6. I can't cut anything more than 6 inches. And now I don't want to drag up. I want to see what's way up there. So I go to my menu, my window settings, and I want to change my Y maximum to, let's try 200 again. No, not quite, but close enough. I can kind of drag it up. If you have an 83 or an 84, you'd have to go back to the window and change it from 200 to like 400. But there it is. And I find this maximum. Remember, the Y value represents the volume because that's what we wrote. the volume equals all of this. So the y value is the volume, and I want to find the biggest volume. So I go to Analyze Graph, maximum, the lower bound, the upper bound, and the largest possible box would have a volume of 263 cubic inches. And that occurs when I cut out 2.43 inches on each corner. So the greatest possible volume is 263. There's no way with this 12 by 20 sheet of metal you could get a bigger box than 263 cubic inches. No mathematical way, no possible way. What are the dimensions? Well, the height is 2.43 because remember that was the x. The x is the height. The width is 12 minus 2 of those x's. And the length is 20 minus 2 of those x's. So the dimensions are here. 2.43 inches high, 7.14 inches wide, and 15.14 inches long.